In this lesson, we're going to learn two different pieces. One, how to write an equation given a complex zero, and two, something called Descartes' rule of signs, which we'll get to in the second part of the video. Our first topic is a bit of review from what we saw writing equations of polynomials. Remember, complex zeros and radical roots always come in pairs. We're either using the opposite or the conjugate. Starting off with the real zeros, our function will equal putting those zeros into the binomial with x, making them opposite. So instead of -1 plus 1, we have that one twice. And then we have an imaginary zero of 3i. So we put that into the asylum with the x, and we use its opposite. In this case, 3i does not have a real part, so we don't need to do the conjugate, we simply need the opposite. In order to write this in standard form, I'm going to FOIL the two pieces that match. So I'm going to FOIL my two binomials with real zeros. So we have the x squared plus 1x plus 1x plus 1. And then FOILing my two pieces with imaginary zeros, x squared. Because they're conjugates, I can skip the inner and outer and just multiply the first and the last. So minus 9i squared. Simplifying this first piece, we get x squared plus 2x plus 1. Simplifying the second piece, remember I squared is -1 times the 9 is a positive 9. I'm still getting a few people trying to factor x squared plus 9 into either x plus 3 times x plus 3, x minus 3 times x minus 3, or the conjugates x plus 3, x minus 3. You can clearly see from this example that it comes from imaginary roots. A sum of squares does not factor into real roots. Now we can't FOIL because the first set of parentheses is a trinomial. FOILing is very specific to binomials. So we will use the distributive property. I'm going to multiply my x squared by x squared, multiply the x squared by positive 9, and then I'll distribute my 2x times x squared, and 2x times 9. And then I'll distribute my 1 to the x squared and to the 9. Finally, we'll combine all of our like terms. We have a 2x cubed that does not have a like term. 9x squared plus x squared gives us a total of 10x. Plus our 18x does not have like terms, plus our 9 does not have like terms. Our next example is to determine all of the zeros knowing that we have a complex zero. We're going to set this up with synthetic division. 1x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. We are given the zero, so we do not make it opposite. We use the zero on the outside. Dropping the 1, multiplying by the 1 minus 3i. Adding. Remember, when you add here, you can only add the like terms. So I will add my -3 to my real number of 1 to get -2. The minus 3i stays as a -3i. Now when I multiply my 1 minus 3i, my 0, by the result that I got when I added -2 minus 3i, I will need to FOIL. 1 times -2, 1 times -3i, -3i times -2, and -3i times -3i. I'm going to combine my like terms and write the result under my 6, which is the next piece in my synthetic division that I will have to add to. So the 9i squared becomes -9, adding it to my -2, and the -3i plus 6i gives me a 3i. Adding my real numbers together, 6 minus 11, plus my 3i. FOILing again with my 0, this time I'm FOILing by 5, -5 plus 3i. 1 times -5 plus 1 times 3i, -3i times -5, and -3i times positive 3i. I needed to give myself a little more room there. The -9 times I squared becomes a positive 9, plus the negative 5. And the 3i plus 15i gives me an 18i. Adding my real numbers together, multiplying that result by the 0. 1 times 6, 1 times 18i, negative 3 times 6, and negative 3i times 18i. Negative 54i squared becomes positive 54, plus the 6 gives me a 60, and the positive 18i and the negative 18i cancel, which is exactly what we need in order to show that the remainder is 0, so that 1 minus 3i is a factor of the function. When you are told that a value is a factor, you should get a remainder of 0. If you do not, go back and find your mistake. There's a lot of algebra on this. There's a lot of different places that you could have made a mistake, so be sure to check your work carefully. Knowing that complex zeros always come in pairs, I'm going to divide by the conjugate of the 0 we were given, 1 plus 3i. Dropping the 1, multiplying by the 1 plus 3i. This time we have like terms to add. We'll add our real numbers as well as our imaginary numbers. In this case, they canceled, so that worked out pretty nicely. Multiplying the negative 1 by the 1 plus 3i, we get negative 1 minus 3i. Adding our like terms, our imaginary pieces cancel again. Multiplying that negative 6 by the 1 plus 3i. Adding our like terms, we get 0. Again, we got a remainder of 0. So this shows that the conjugate is also a factor of the function. If you do not get a remainder of 0, go back and check your work. We found 2 zeros of the function. To find the rest of the zeros, we will take this result. We started with a power of 4, and we have divided twice. We need to drop 2 powers when we write this result. Setting it equal to 0 to finish finding the zeros of this function. T-chart factoring, what multiplies to a negative 6 and adds to a negative 1 would be a positive 2 and a negative 3. Setting each of those binomials equal to 0 and solving. For the complex zeros, I would not write those as an ordered pair. We do not graph imaginary zeros on a real coordinate plane. So we had 2 imaginary zeros, 1 plus 3i and 1 minus 3i. And then we had the 2 zeros that we can write as an ordered pair that we would graph on a coordinate plane if we were graphing this function. Final piece of this lesson is Descartes' rule of signs. What this does is give us the maximum number of positive or negative zeros that a function can have. So it's helpful when you're using the rational root theorem. It gives you an even better chance of guessing a correct zero. The second piece here, so for positive roots, count the number of sign changes in the function itself. So when a term goes from positive and the next term is negative, that's a sign change. So that would give us a potential positive 0 of the function. For negative zeros, you substitute negative x into the function and then count the sign changes. Our last example, we're going to use Descartes' rule of signs to determine the maximum number of positive zeros and the maximum number of negative zeros for this function. Our first term is positive, our second term is negative, our third term is negative, and our last term was positive. So looking at the number of sign changes, we have a sign change from positive to negative, and then there was not a sign change, it stayed negative, and there was another sign change from negative to positive. So we had 2 sign changes, so there are at most 2 positive zeros. So there could be 0 positive zeros, there could be 1 positive 0, or there could be 2 positive zeros. To find possible negative zeros, we substitute negative x into the function, replacing all of the x's with a negative x. and seeing what happens to that negative sign. So our first term is negative x cubed. That negative will stay negative, so it becomes negative 4x cubed. Our second term, the negative x squared, will become positive, so we stay negative 5x squared. Our third term, the negative times negative, will become positive, and of course our 2 stays positive. So the signs on this are negative, negative, positive, positive. This time between our first two terms, the sign stays the same. Between the second and the third term, we have a sign change, and then it stays the same again. So we only have one sign change. So we have 0 or 1 possible negative roots of the function. You have 2 U-Try questions on this one. Please make sure you bring all of your questions to class.